Hi friends, welcome to our channel. Today in this episode we are going to discuss equivalent circuit of three-phase induction motor. One thing you must be noted that three-phase induction motor acts as a generalized transformer, because if three-phase AC supply is given to the stator winding of three-phase induction motor, a rotating magnetic field is developed, and due to that rotating magnetic field means the flux, resultant flux which is produced, and due to that resultant flux EMF is induced in the rotor winding and it produces the current. So electromagnetic induction takes place in three-phase induction motor also. So induction motor may act as a generalized transformer. So if we discuss about equivalent circuit of three-phase induction motor first. So we can say that equivalent circuit of three-phase induction motor is similar to that of transformer by some proper arrangements. So we have to do here arrangements. First, tell me that what is the difference between transformer and induction motor? The only difference is that secondary winding of induction motor, that is rotor, is dynamic, means it is rotating and is short circuited. Okay, and all the other things are common to both induction motor as well as transformer. So if only one difference is occurring in the secondary winding of three-phase induction motor, primary winding of three-phase induction motor equivalent circuit is similar to that of transformer. We can say that. Okay, so first draw the equivalent circuit of stator, that is primary winding of three-phase induction motor, that is stator. So see here, resistance R1, leakage reactance X1, this is shunt branch which we have seen in the transformer, R node, X node, R1, X1. The current flowing through this shunt branch is I node. Current flowing through these components is IW, and current flowing through this X node is I mu. Okay, and this is the primary winding of transformer and also the induction motor, that is stator. We can say that because stator winding and primary winding of transformer are similar to each other, because only difference is occurring in the secondary winding of three-phase induction motor as compared to transformer. Current flowing through this primary winding is I1. Here I0 current is flowing, that is no load current. So here the current flowing is load component of reflected load component of secondary winding, means reflected secondary current is flowing through this branch, means I2 dash current is flowing here, and the applied voltage to the stator winding is V1, which we apply voltage to the primary winding of transformer. It is similar to that. This is the applied voltage V1 which we apply to the stator winding of three-phase induction motor, and EMF induced in the stator winding we can given it as a E1, EMF induced in primary winding. And what about supply frequency, means what about frequency? So here F is equals to supply frequency in stator, because in stator there is constant frequency of 50 Hertz which is supply frequency. Okay, so R1 is stator resistance per phase, X1 is leakage reactance of stator per phase, I node is no load current per phase, R node is the component for supplying the core losses, and current flowing through this R node is IW, that is working component of no load current. And what about X node? X node is the component which is used to produce the flux between stator and rotor, means in the air gap, and current flowing through this component is I mu, that is magnetizing component of no load current. Due to this magnetizing component of no load current, the flux is produced. And these all the currents are per phase. Okay, per phase. And what about this? This is the stator winding of three-phase induction motor per phase. And what about these currents? I1. I1 is the current flowing through the stator winding of three-phase induction motor, and in which the current is distributed. I0 means I0, no load component, no load current, and I2 dash. I2 dash is reflected current of secondary winding or rotor winding of three-phase induction motor. V1 is the applied voltage to the stator winding per phase, and E1 is the EMF induced in the stator winding per phase. And frequency of supply given to the stator winding is of supply frequency, which is nearly 50 Hz. Okay. Now if we see in the transformer, the secondary winding is also of the same frequency as that of primary winding. Means transformer is a static piece by means of which electrical power is transferred from one electrical circuit to another alternating circuit. We change in current and voltage but without change in frequency. But what about in three-phase induction motor? In three-phase induction motor, the frequency of rotor winding is changed due to change in the value of slip. So if we have to make the induction motor equivalent circuit similar to that of transformer, we must make the rotor frequency which is equals to supply frequency by some arrangements, and this arrangement we should follow now. Up to now, the three-phase induction motor equivalent circuit is not similar to that of transformer. So first we have to make the frequency of rotor winding which is equals to supply frequency, means which is as that of stator. When stator frequency and rotor frequency are both becoming equal by making some arrangements, then three-phase induction motor may act as a generalized transformer, means equivalent circuit of three-phase induction motor is similar to that of transformer. We can say that by making some arrangements. And equivalent circuit of stator is same as that of equivalent circuit of primary winding of a transformer. So if some by proper arrangement we have to make the rotor frequency equals to stator frequency, then what should be the arrangement? We know that current flowing through rotor winding in running condition is IR2. We have seen it in the last lectures of three-phase induction motor. So IR2 is equals to ER2 by ZR2. We are seeing that, where IR2 is rotor current per phase in rotor winding, ER2 is induced EMF in the rotor per phase, and ZR2 is impedance of the rotor per phase under running condition. So what is ER2? ER2 is equals to slip times rotor induced EMF per phase under stationary condition. So SE2 divided by ZR2. What is ZR2? ZR2 is under root R2 square plus S into X2 bracket square, where R2 is resistance of rotor per phase and X2 is reactance of rotor per phase under stationary condition. But where it is a slip S, so S into X2 means XR2, means this reactance is in running condition now. Okay. And we can also write this equation as S into E2 divided by R2 plus J S X2, R2 plus J S into X2. Okay, both equations are same, both are similar. So now divide numerator and denominator by S. So divide numerator and denominator by slip S. So after dividing numerator and denominator by slip S, we get E2 divided by R2 by S plus J into X2. Okay, E2 divided by R2 by S plus J into X2. So that arrangement we have to make here in the equivalent circuit of rotor. By making that arrangement, we can get that the reactance, rotor reactance per phase is not belongs to slip S, means rotor reactance not depends on slip S, then EMF induced in rotor not depends on slip S, only rotor resistance per phase depends on slip S. Actually rotor resistance per phase is constant, and these all the parameters are varying. Rotor induced EMF per phase, reactance per phase, all these parameters are varying, but by making some arrangement by dividing numerator and denominator by S, then we can say that the E2 and X2 is not now depends on slip only for drawing that these equivalent circuit, but actually it depends on slip, and this rotor resistance per phase is also not dependent on slip, but we make the all things reverse here to draw the equivalent circuit of three-phase induction motor, which is similar to transformer, by making the frequency equal. So see here, if the X2 is now not dependent on slip, we remove the slip and only here slip is applied by making some proper arrangement. Only slip is applied. Means rotor resistance per phase depends only on slip, and all other things are not dependent on the value of slip. So by this equation we can say that the frequency of rotor is also not depends on slip. Means after when you start the motor, the slip value is 1, and slip value is reducing when the motor catches the speed, and so due to that slip frequency is also reducing, we know that. But by making some proper arrangement only for drawing the equivalent circuit of rotor similar to that of transformer, here we make this arrangement. So here the frequency, now rotor frequency is becoming a supply frequency only for drawing the circuit similar to that of transformer. Because if this X2 is now constant, then X2 is equals to 2 pi FL2. Okay, so 2 pi F dash L2, we can say that, because F dash is rotor frequency. So 2 pi F dash L2. So if this X2 is constant, then F dash, frequency F dash is also constant, which is equals to supply frequency. So by making this equation, we can make supply frequency apply to the rotor. So means rotor frequency is equals to supply frequency. We can make this by this equation. Now see here, when the rotor frequency is not constant, then what is the actual equivalent circuit of rotor, that you must see first, and then apply this equation which we have find here. So actual equivalent circuit of rotor, so we can draw it. So equivalent circuit of rotor means secondary winding. So it is R2, rotor resistance per phase R2, reactance, rotor reactance per phase X2, and here not any electrical load is connected here, and the rotor is short circuited. We know that rotor is short circuited here, so this is the short circuit path, and the voltage applied to the means EMF induced in the rotor comes here first, which is ER2, that is equals to S into E2, slip times rotor induced EMF under stationary condition. So rotor induced EMF under running condition is equals to slip times rotor induced EMF under stationary condition. We have seen it already, and this is rotor resistance per phase R2, and this is rotor leakage reactance per phase X2. But which parameter is varying in the rotor? R2, rotor resistance R2 is constant, it is not varying. But what about X2? Rotor leakage reactance X2 is varying continuously with the change in value of slip. So up to the slip S becomes constant, this reactance of rotor per phase is varying with this slip. So here we can say that rotor reactance X2 is depends on slip. So here S into X2, we can say that X into X2, and this rotor reactance is variable in the actual equivalent circuit of rotor. And what about frequency? So here frequency F is means frequency F dash, we can say that frequency F dash, because this is the rotor frequency and we denote the rotor frequency as a F dash. So frequency F dash is equals to S into F, slip times the supply frequency. So frequency is now dependent on slip, and to make the frequency and this rotor reactance independent and rotor resistance per phase dependent, means reverse, we have to do the reverse things. So by making these all the reverse things, we can draw another equivalent circuit by making by this equation IR2 is equals to E2 by R2 by S plus JX2. So this new rotor equivalent circuit which we will get, in that equivalent circuit this slip S is removed for these reactance, rotor reactance X2, means rotor reactance X2 becomes constant, frequency of rotor is equals to supply frequency, it will become also constant, and only what is varying, rotor resistance per phase is varying in that equivalent circuit. And why we make such arrangement? To make the three-phase induction motor equivalent circuit is equals to transformer equivalent circuit, means to show the equivalent circuit, means a three-phase induction motor acts as a generalized transformer. To show that, we must say that equivalent circuit of three-phase induction motor is similar to that of transformer, and to make that arrangement we should follow this method. So by this actual equivalent circuit of rotor, we can draw the modified equivalent circuit of rotor. See here. So by this equation, all the parameters are independent on the value of slip, and only rotor resistance becomes dependent on slip. So what is the new equivalent circuit? It is the rotor resistance per phase is dependent on slip, and which is R2 by S now. So R2 by S, and it is variable, so we can make that variable sign here. And reactance, leakage reactance X2 is now not depends on slip, so here not comes S into X2, X2 becomes constant here, so only X2 comes, and this is the short circuit path. And here only rotor induced EMF E2 now, not ER2, because all the things are not dependent on slip, only rotor resistance is dependent on slip. We make this arrangement only for our convenience. Okay, so this is rotor induced EMF per phase under stationary condition. So here what is the current? This is not IR2 now, IR2 is equals to I2, means rotor current under running condition is equals to rotor current under stationary condition by making our arrangement. So now we can say here it is only I2. And what about frequency? Once this rotor reactance per phase is constant, so our rotor frequency F dash is also constant. So F dash is also equals to supply frequency of stator now. Okay, so by this our arrangement we can get this modified equivalent circuit of rotor. Now we can also modify that modified equivalent circuit of rotor by making that arrangement is R2 by S is equals to R2 by S plus R2 minus R2. So by making this arrangement R2 by S plus R2 minus R2, which is equals to R2 by S, we can get R2 in bracket 1 by S minus 1 plus R2. Means this is rotor resistance per phase constant, and this rotor resistance per phase depends on the value of slip. Means we have two rotor resistances here. This is rotor resistance per phase constant, and this rotor resistance is varying, which is equivalent electrical load. Means electrical equivalent of mechanical load. We can say this thing as a equivalent electrical load of the mechanical load. Means equivalent electrical load of mechanical load, or we can say that electrical equivalent of mechanical load. So now we can draw final equivalent circuit of rotor. So what about final equivalent circuit? We can write R2 by S is equals to R2 in bracket 1 by S minus 1 plus R2. So here rotor resistance per phase also becomes constant, R2, these R2, this, okay, and rotor reactance X2, and one more resistance which is load resistance, we can say this, which it is variable resistance. This is R2 in bracket 1 by S minus 1, electrical equivalent of mechanical load, and now the circuit is completed. And this is rotor induced EMF E2 as usual, and current flowing through the rotor is I2. So all the things are now independent of slip except that load which we have connected here. So this load is electrical equivalent of mechanical load. So only this is varying. So here frequency also F dash is equals to supply frequency. So now we can say that the equivalent circuit of three-phase induction motor is just similar to that of transformer now. So by making that arrangement, we have make this arrangement. Okay? For achieving that equivalent circuit of three-phase induction motor similar to that of transformer. So now this is the final modified equivalent circuit of rotor. Now after drawing the equivalent circuit of stator and as well as rotor, and by combining these equivalent circuits, both equivalent circuit of stator and rotor, we can get complete equivalent circuit of three-phase induction motor, which we can see here. So see here, this is equivalent circuit of stator and this is equivalent circuit of rotor, and by combining these both circuits, we can get complete equivalent circuit of three-phase induction motor. R1 is stator resistance per phase, X1 is leakage reactance of stator per phase, I0 means I0 is no load current per phase, IW is working component of no load current per phase, I mu is magnetizing component of no load current per phase, R0 is used for supplying the losses, and X0 means X0 is for producing the flux in the air gap between stator and rotor. E1 is induced EMF in stator per phase, V1 is applied voltage to the stator per phase, I1 is current flowing through the stator per phase, I2 dash is reflected secondary current, reflected rotor current per phase, I0 means I0 is no load current per phase, I2 is rotor current per phase, R2 is rotor resistance per phase, X2 is leakage reactance of rotor per phase, and this RL, that is equals to R2 in bracket 1 by S minus 1 is electrical equivalent of mechanical load. And supply frequency to both stator and rotor is now equal. So by making the supply frequency equal, so we can say that the three-phase induction motor may act as a generalized transformer now. Now can we draw the equivalent circuit of three-phase induction motor referred to stator? So we can draw it by shifting these rotor parameters in the stator side. So what is the rotor parameters? R2, X2, RL in the rotor side. So what it will becomes? It will becomes R2 dash, X2 dash, and this is RL dash by after shifting these parameters into primary side, that is stator side. So we can draw the equivalent circuit referred to stator. So this is the equivalent circuit of three-phase induction motor referred to stator side, means referred to primary side. So all these parameters of rotor side is shifted to primary side by becoming R2 dash, X2 dash and RL dash, and all these parameters remain same in primary winding. So what is the value of R2 dash according to transformation ratio? In transformer we also seen that the equivalent circuit of a transformer referred to primary winding. So similar to that, the R2 dash is equals to R2 by K square according to transformation ratio, X2 dash is equals to X2 by K square, and RL dash is equals to RL by K square, means R2 dash by R2 by K square in bracket 1 by S minus 1. So we can write this value, R2 dash is equals to R2 by K square, X2 dash, this X2 dash is equals to X2 by K square, and this RL dash is equals to RL by K square, means R2 dash by K R2 by K square in bracket 1 by S minus 1. So this is the complete equivalent circuit referred to stator. Okay. And what about the rotor induced EMF of secondary winding with respect to stator, means primary winding? It is E2 by K. Here we get the rotor induced EMF per phase, which will equal to E2 by K if we have to draw the equivalent circuit referred to stator. So here E2 by K is also drawn. Now can we draw the approximate equivalent circuit of three-phase induction motor? So of course we can draw it by shifting this shunt branch, means no load current branch, to the left side, and by R1, X1, R2 dash, X2 dash combining together. So we can make that circuit also. So this is the approximate equivalent circuit of three-phase induction motor by shifting this shunt branch towards left side. So here current is I1, here it is no load current, I2 dash is reflected rotor current in the stator, I2 dash, and this I2 dash is flowing through all these components now, R1, X1, R2 dash, X2 dash, and this is R2 dash in bracket 1 by S minus 1 means RL dash. We can say that it is the electrical equivalent of mechanical load, and here it is the stator induced EMF per phase E1, and rotor induced EMF E2 is given by E2 by K in the stator. Okay. Now we can analyze the three-phase induction motor equivalent circuit now. At no load condition of three-phase induction motor, N is approximately equal to Ns. Not exactly equal to Ns, but assume that it is approximately equal to Ns. So when N equal to Ns, slip S is equal to 0. We have already seen in the last lectures. So S equal to 0. So now put S equal to 0 in RL dash. Put S equal to 0 in RL dash. This is your whole RL dash. So put S equal to 0 here. So if we put the S equal to 0, so in no load condition, if we put this S equal to 0, 1 by 0, it goes to infinity, means 1 by 0, infinity minus 1, infinity. So this whole resistance is tends to infinity. So R2 dash becomes infinity. So at no load condition, if R2 dash is treated as an infinity, means no any current is flowing through this electrical equivalent of mechanical load, then at that time this secondary means this load is open circuited, means this winding is open circuit, means we can say that secondary is treated to be as an open circuit. Okay, when at no load condition, N equal to Ns, S equal to 0. At that case, R2 dash it tends to infinity. Now we can analyze the three-phase induction motor and in the case of starting. So when N equal to 0 means when speed equal to 0, slip is equal to 1. We have already seen this. So slip equal to 1. So now we can put slip S is equals to 1 in the R2 dash. Means RL dash is equals to R2 dash in bracket 1 by S minus 1. Okay. So if we put S equal to 1, so 1 by 1 minus 1 means 0, means this RL dash it tends to 0, means no any resistance is to be inserted in the rotor winding in the at the time of starting. So at that time, by analyzing this, we can say that this secondary winding is treated to be as a short circuit path in the case of starting. So we analyze this three-phase induction motor at the time of starting and when N equal to Ns, means at no load condition also. So analysis of three-phase induction motor is also done here. So now if the three-phase induction motor is just similar to that of transformer, vector diagram of transformer is applicable to three-phase induction motor also. Except that slip comes here in three-phase induction motor, in transformer slip not comes. So this is common, flux phi, magnetizing component of no load current. We have already seen in the transformer this phasor diagram. I node no load current, IW working component of no load current, and this whole IW and I mu resultant is I0, and this is the reflected secondary current IR2 dash. We can say it as a IR2 dash, and by combining these IR2 dash and I0 we can get I1 current flowing in the stator winding, and exactly opposite to that IR2 dash, current in secondary starts flowing. So this is IR2 current starts flowing exactly opposite to that IR2 dash. So in secondary winding this IR2 current flowing at running condition of rotor, and at running condition of rotor, what is the resistance? IR2 into R2, means current flowing through the resistance, and it is in a phase because resistance is so current flowing through this resistance. So in phase IR2 dot R2, IR2 into R2 in a phase with IR2, and IR2 into IR2 SX2 is exactly 90 degree with respect to IR2. So it is 90 degree with respect to IR2, and IR2 into R2 and IR2 into S into X2, we can get it as a IR2 ZR2. Okay, and this is ER2 is equals to S into E2, E1 stator induced EMF per phase, E2 rotor induced EMF per phase, but it is not E2, it will ER2 because rotor induced EMF per phase under running conditions. So ER2 is equals to S into E2. And what about this I1 R1? This is in a phase with this current I1 because here resistance R1 we have shown here. So I1 R1 current flowing through this stator winding stator resistance, it is in a phase with this I1. And what about this I1 X1? I1 X1 is 90 degree leading to this I1 R1. So this is the I1 X1, I1 R1 and I1 X1 relations to 90 degree with respect to each other. And this I1 R1 and I1 X1 combining to get I1 Z1. And this is the V1 voltage applied to the stator V1. So this is the complete phasor diagram of three-phase induction motor, vector diagram of three-phase induction motor. And we can get these equations. V1 is equals to E1 plus I1 Z1, E1 plus I1 into R1 plus JX1 by equivalent circuit of stator. And ER2 is equals to VR2 plus IR2 into Z2. That is equals to V2 plus IR2 in bracket R2 plus JSX2. So E2 is equals to V2 plus I2Z2. We can also say in that case now. So today we have discussed the complete description about the equivalent circuit of three-phase induction motor. In the next lecture, we are going to discuss the power flow diagram, power stages of three-phase induction motor.